Simon Jeffrey from Armagh Observatory, Senior Research Astronomer there. He's going to talk about astronomical research, small telescopes in an urban environment. And I hope that doesn't lift the water up. Thanks very much, Simon.
Okay.
Thanks very much. Good afternoon, everybody. I think my talk is going to be slightly less about light pollution and more about what we would like to do so long as we keep the light pollution low. But it's to give you but another aspect of it is to give you an idea of what we are doing in Armagh and why we want to keep lights in Armagh as low as possible. And this talk really starts, we'll cover 4 major sections. I'm going to talk about the telescopes in Armagh. I'm going to talk a little bit about the potential for astronomical research from a site such as ourselves. And then I'm going to be talking about 2 projects, the Polar Bear Survey Telescope, and I'll tell you more about that, and the Armagh Variable Star Telescope. First of all, what about the history of astronomy from Armagh? And some of you may have heard already that we have a 200-year history of observational astronomy from a site very close to here in what is now a city centre location. It starts with the Troughton 5-centimetre equatorial, and as you will see from the apertures of these telescopes, and I will show you them in a moment, they start off as very small, modest devices, and they get larger until we come 1990 to the Calver 45 centimetre. And then there is a break because during this period lights got brighter, and people recognized that larger telescopes were expensive, and the weather in Armagh was not a great place to put an expensive instrument. And so this 80-centimetre telescope, built in collaboration with the Dunsink Observatory and the Harvard Observatory, went to South Africa. And indeed, our latest collaboration is again in South Africa with a 10-metre telescope. And just to give you a flavour, if you haven't been for a walk around the observatory of these instruments, here is the oldest instrument, the Troughton Equatorial. Here is our Mural telescope, and then these successively larger instruments. This is the Calver, and this is the 80-centimetre ADH telescope. And just to bring you up to date, here's a picture of the 10-metre telescope in South Africa. But as was fairly obvious, there's a recognition during the 20th century that that climate was not conducive to observing from Northern Ireland, and light pollution has an increasing adverse effect on local observing as well. So major research has shifted to space and island mountain observatories. And the Armagh telescopes have fallen mostly out of use. In 2003, we had a major restoration project, and today the 30-centimetre grub is usable for optical viewing, and the 45-centimetre has had a CCD television camera attached. But these are still old instruments, and so from the point of view in pursuing research, they're still not ideally suited. So is it sensible to talk about attempting to do astronomical research from a site such as Armagh? Now, one reason why we might want to do this is because the site is accessible. It's convenient. We can build our equipment there. We can go to it, and so that convenience reduces the cost, or some of the major costs of doing research. And of course, if you have your own equipment on site, it's available to you all of the year round. The other thing, the question of accessibility, is accessibility of the sky. Now, light pollution isn't the only thing that disturbs astronomers. One of them is the quality of the atmosphere, and that's the seeing. And from a place like Armagh, as far as I'm aware, our seeing is probably limited to being greater than 2 arc seconds. That's the size of a point source. Although we don't have a good measurement of that locally for a good night. The light, which is the sky background, which I measured first of all last year, and I did actually repeat this measurement a couple of nights ago, and in astronomical terms, and this was done with a sky quality meter, we have a measurement of 19 magnitudes per square arc second. That is a city centre measurement. I went home on Wednesday evening and made the same measurement from home, which is 1 kilometre to the east of here, and got nearly 1 magnitude better. It was 19.9. And Mark Bailey tells me that from his house, the measurement is about 21. And that's in a rural site 20 kilometres away. So and that represents a difference. 1 magnitude is roughly a factor of 2 to 3 in brightness. So it's not great, but it's nothing like Belfast. The other factor is cloud. Is it worth actually spending money on equipment and putting it in place? How much time are you actually going to spend on target, looking at the sky? And when this came up, this was actually in discussion of a light pollution project some years ago, I did a quick calculation. We have available to us in Armagh weather records, including sunshine records, going back for over 100 years. Now, the sun is above the horizon for approximately 4,400 hours in the course of a year. Our sunshine records show that that the sun is visible, that it is shining, for 1,250 hours of the year. So I suppose that's the depressing bit of news, is that it's actually only sunny for less than 1/3 of the time. However, if you then look at the number of dark hours per night and say that if you take any random part of the sky and say it's going to be clear for that same fraction, and that may not be a completely correct assumption, but it's a good working hypothesis, that we have basically about 1,040 clear hours. Or in observing nights terms, that's 104 nights. Now, any astronomer, if you told any astronomer that he could have 104 nights on a telescope, he would say, wow. So actually, if you could manage your time in such a way that you could use those 104 nights, you'd be doing very well indeed. Now, of course, in the olden days, the astronomer, in order to use all of those 104 nights, would have to spend all 365 nights up all night waiting for a short gap in the cloud and saying, it's clear, I can go. And then when it clouds over half an hour later, he says, all right, I've collected that data, I'll keep that for later. And that's not a good way to work. But we live in an age, in a very robotic age, and so the idea was that if we could attempt to operate our telescopes basically automatically so that they could use all of the time that was available as optimally as possible, then we could recover these 104 nights observing per year. What sort of science can you do if you are given that sort of facility? Well, my main area of interest observationally, one of them turns out to be in the area of time domain astrophysics. Now, I've just given up a list of obscure objects, of topics there which are rather technical. I'm going to summarize that with a slide which has a number of different light curves on it. And these are sorts of different things that you can look at in the sky, different types of star. that stars are variable on all sorts of different timescales. Some of them, this is a short period binary. This is AMCVN. It's a pair of white dwarfs which are orbiting one another. These are stars which are half the mass of the Sun, but they're orbiting one another within a volume the size of Saturn. So these vary on timescales of 15 minutes or 20 minutes or so. Whereas Myra is a supergiant, a red supergiant, and it varies on the timescale of 3 years or so. Actually, this area of time domain, astrophysics, is very much understudied because you don't get long periods of observing time on big telescopes. You rely on doing this sort of work from small telescopes where you have long observing times. This is a light curve of an asteroid which is spinning. This is the light curve of a planet passing in front of a star. This is actually an observation that was made from Ireland. This is the minor planet Eris, or dwarf planet Eris. It was the first observation from Ireland of this planet. Actually, the telescope was not in Ireland, but it was operated from here. Okay, so that's some of the things that we might do with it, might do. And this provoked, first of all, an idea for a project. Mark Bailey asked me, how would I design a light pollution monitor? And of course, I got it all wrong because I thought what I need is a standard star, something that I can calibrate the sky brightness against. And I thought, well, we've got Polaris, and that's always there. Let's just point a telescope at Polaris and monitor that all the time. And by the way, we'll be able to look at all sorts of other stars as well, because if we make our field wide enough, we can do all sorts of things. And we can maybe monitor lots and lots of different stars for variability. And so this gave us the concept of a fixed cameras with a significant field of view, which will run all the time. And these are the bits and pieces of it. That's the telescope, which is a camera lens. That's the camera, which is a CCD camera. This is the housing, which is a video camera housing, because it's going to work all night. And this is it in situ, the bits bolted together in the observatory under test. This is its location on the observatory roof. And you're probably wondering, why is it called the Polar Bear Telescope? Well, the reason for that is at the top of here. We're pointing at this star here, Polaris. This is the constellation of Ursa Minor, the little bear. And so this is a polar bear. Oh, all right. Well, I like the idea. This is the operating equipment. Each camera is operated by a mini computer. It took some time to get the alignment right, but basically we have 3 overlapping fields of view with the celestial pole, which is not quite where Polaris is, right in the middle here. And so during the night and during the year, the field rotates around it. That is one field, and you can see Polaris here, which is completely burnt out. And so far, we're not able to use that. We go down to about, well, here's a section of the field enlarged. And this is exactly the same image, but I've just processed it slightly differently so that you can see just how faint we go. We go down to about 12th or 13th magnitude with a lens this size in 30 seconds, which is quite staggering. This is a movie which is made up of frames taken one per night around about midnight. And what it will show you, actually the nights where we got no stars, or frames with no stars, don't appear. But it will give you a picture of the sort of time behavior of the sky above Armagh. There's a good night, then there'll be nights where there's sort of a bit of haze, and there'll be nights where you see patchy cloud and all sorts of things going on. This is a sample of a small number of light curves for different stars, and this is one night or 14 hours, and you see the light from one star, and the standard deviation is of this star, which is nearly ninth magnitude, is 0.036 magnitudes. This is a series of light curves of one individual star. I was desperately looking earlier in the week to see if I could find a really variable star, a nice short-term variable star that you would say, wow, I can see everything happening. I'm afraid that what you can see is there's a good night, and there's a not-so-good night, and there's a good night, and there's a very, very, very bad night. And all the nights in between were even worse. There was no data for those. So this is a project that's up and running. We have gathered a year's worth of data, a huge number. There's something like 10,000 stars, something like 3,000 frames per night. So you can imagine just what sort of volume of data we have to deal with. It was a predecessor, though, for a new initiative. The Department of Culture, Arts and Leisure, our funders, announced an opportunity at the end of last year of some capital funding, and they gave us outline approval to extend that for another year or so. And so we thought that in order to make most use of this capital, we would initiate a project to build a new telescope in Armagh. And, well, I know that Terry's going to make me sit down and shut up very, very soon. So you can read the goals. I'll show you a picture of the telescope that we've bought and the mount, and a picture of the dome that we're going to buy. Well, it isn't this one because this is the desert, and it isn't this one because we virtually never get snow. Well, we'll see what it's going to look like. We have the camera, and we have various other bits and pieces. This camera will give us a very large field of view, and nearly 50% quantum efficiency, and it's going to go round about here in the observatory, and that's I want you just to switch all your lights off and let us get on with doing some excellent astronomy.
Thanks very much, David.